Right now our panel will be in English and we will talk about rise of scalability technologies, and we'll have PhD student from Stanford University, very bright star of our ecosystem. So I'd like to invite Ertem Nusret Taş. Welcome, dear friend. Have a good day. How are you? Hope you everything all right.
So hi everyone. I am Ertem Nusret Taş, and the topic of the presentation is accountable safety for rollups, one of the prominent recent scalability technologies. So this is actually a paper, and these are my co-authors. They are John Adler, Mustafa Al-Bassam, Ismail Kofi, Nima Waziri, and my advisor David Che from Stanford. Okay, without further ado, let's start. So I would like to first start with the key takeaways in case you need to run away and I don't want to listen to the rest of the talk. So the first key takeaway we have here is that the security of the rollups has typically been shown trusting an honest majority on the parent chain. So these rollups derive security from a parent chain, and their security has been shown under an honest majority assumption. However, in this work, we would like to attain a trust minimizing notion of safety and get rid of this honest majority assumption. Now, trust minimizing means different things to different people, but here we will mean accountable safety, which I will shortly define as a correct notion of trust minimizing safety. Now, our main result is that the rollup users, in order to attain accountable safety, they should validate the rollup state and check for data availability. And we will show why this is a requirement. Okay, to give meaning to all of these words, let's take a step back and start with blockchain protocols. So here, when I mention blockchain, I mean a state machine replication protocol where transactions are batched into blocks. Now, there are three main requirements for a blockchain protocol. You can also think of these as ingredients for it. The first one is consensus, which means that the validators of the protocol should ensure that the observers of the protocols, that I will later call clients, output these transactions in the same order. They agree on the ordering, and this is a total order. Now, the second main requirement is data availability, which means that the validators should ensure that the clients can access and download any transaction that has been finalized if they wish. And the third one is execution, that the validators should basically execute these transactions and update the state of the system. And typically what they do is that they take a succinct commitment to this state, such as a Merkle root, and put it into the headers of the blockchain. Now, how does a rollup fit in this paradigm? So what I've described were the three main ingredients for a monolithic blockchain, but these also apply to a rollup. But the rollup itself is a layer 2 scalability solution for these blockchains. And it consists of two main pieces. The first one is the parent chain. The parent chain is responsible for the ordering and availability of the rollup transactions, and is maintained by entities that I would like to call the parent chain validators. So these parent chain validators receive rollup transactions from the environment. They order those, and they make these available for the observers of the rollup. Now, the second main part of the rollup is what I would like to call a rollup chain. And it consists of these rollup blocks that are produced by sequencers. So these sequencers receive rollup transactions again from the environment, such as the clients of the rollup. And then they batch these transactions into rollup blocks. They execute the transactions in a rollup block and obtain the new state and put the commitment to this new state to, let's say, the header of the rollup block. Now, the crux of the rollup paradigm is that these sequencers are not trusted a priori. Their execution of the rollup blocks are verified by rollup nodes. Now, these rollup nodes can come in two flavors. They can either be rollup full nodes who download these blocks and verify the state commitment within each block explicitly, or they can be rollup light clients that verify the validity of the blocks, the validity of the state commitments within these blocks through lightweight methods. Now, going forward in the rest of the talk, I will focus on the rollup full nodes, and I will keep calling them rollup nodes and sometimes rollup clients interchangeably. Now, that was a lot of words, so let's see this all in a diagram. So here we have our parent chain, and here we have our sequencer. So the sequencers receive rollup transactions from the environment. It batches them into rollup blocks, executes these rollup blocks, obtains the state commitment corresponding to this rollup block, right, and sends this rollup block to the parent chain. Now, in many rollups that exist out there and that are currently being developed, there is a bridge contract on the parent chain. So the rollup is designed with a bridge contract. So this bridge contract verifies the validity of the rollup blocks that are received by the parent chain. And then it accepts the rollup block as part of the parent chain if the block is valid, meaning the state is valid. So bridge contract, of course, doesn't execute all rollup transactions. It does this validity check through lightweight methods such as fraud proofs or ZK validity proofs. Note that there might be multiple bridge contracts run by the parent chain validators in parallel. In this case, the parent chain can act as a host to multiple rollups. But hereafter, I will just focus on a single rollup. Now, the sequencer can be malicious. It can produce invalid blocks, and it can send those to the parent chain, meaning the state is invalid here. But in this case, the bridge contract cannot validate the state, and it rejects the rollup block. And such rollup blocks don't get included as part of the parent chain. And this goes on. And now in these types of rollups, the task of the rollup clients or nodes is very easy. They just have to download the rollup blocks from the parent chain, and they know that these rollup blocks are valid because the bridge contract already made the validity check for them. And then they can simply output the rollup chain as shown here. Now, I call these traditional type of rollups enshrined rollups because the rollup enshrines a bridge contract on a specific parent chain as the ground source of truth. Now, an alternative rollup design is what I would like to call a sovereign rollup, which is simpler in some sense. In a sovereign rollup, there is no bridge contract on the parent chain. So this in particular means that the sequencer, if it's malicious and if it pays the gas fees to of the parent chain, it can send invalid rollup blocks to the parent chain. Now, the burden of checking the validity of the rollup blocks lies with the clients of the rollup or the rollup nodes. So what they would do is that they would download these rollup blocks from the parent chain. They would execute the transactions within each block, and then they will realize this ST2 state, for instance, here is invalid. It doesn't match the correct state obtained after executing the transaction TX2, and they will sanitize this block out of the blocks, out of the rollup blocks downloaded from the parent chain. Now, this is the sovereign rollup paradigm. So let's see now security for rollups. So because rollup is also a state machine replication protocol, its security also rests on the two pillars of security for SMR protocols, which are safety and liveness. Now, as I mentioned before, typically people have shown the safety of rollups, assuming an honest majority on the parent chain validators. Now, there might be some external assumptions, some other assumptions for the safety of a rollup. For instance, in the case of optimistic rollups, there is this network synchrony assumption, there is this existential honesty assumption on the existence of an online watchtower, and so on. In the case of ZK rollups, typically the rollup is assumed to be sound for safety. Now, in the remaining part of the talk, I will try to get rid of this honest majority assumption and replace it with a trust minimizing notion of safety. So for this purpose, let's get some inspiration from the monolithic blockchains. And the notion we would go after is the accountable safety. Now, accountable safety states that whenever there is a safety violation, all observers should be able to provably identify some adversarial validators as protocol violators. In particular, if I say a blockchain has an accountable safety resilience of 1/3, and when there is a safety violation, I should be able to identify 1/3 of the validators as protocol violators, and these should be all adversarial. These should never be honest validators, well, except with negligible probability. Now, note that this is a much stronger notion than proving safety under an honest majority assumption, because countable safety by itself does imply the honest majority, does imply safety under honest majority. But if there are less than 1/3 adversarial validators, of course, they cannot be a safety violation because I cannot identify 1/3 adversarial validators. However, if there are more than 1/3 adversarial validators and they do engage in a safety violation, then everyone can be provably convinced that 1/3 of the validators violated the protocol rules. There are, of course, blockchains that satisfy this property, and this is a recently emerging property. So there is this recent, really nice paper, BFT Protocol Forensics, that proves this for these types of protocols. So let's see how the accountable safety works in the BFT setting. So suppose these are blocks that are finalized, they are voted upon by the validator set of the blockchain. Like these blocks are proposed by a leader, and then the validators vote on the blocks. And if a block gets votes from 2/3 of the validators, it's finalized. Now, if there's a safety violation, this means that there must be two conflicting blocks at the same height that has been voted upon by 2/3 of the validators. In particular, this means that 1/3 of the validators must have double signed both these two blocks. 1/3 must have voted for both of them. However, this is a protocol violation because as part of these protocols, you're not supposed to vote for two conflicting blocks. And then by identifying these double signatures, I can provably identify 1/3 of the validators as protocol violators. Now, this is a super oversimplified setting for these BFT protocols, but this is just to give some intuition how accountable safety could work. Now, how do we generalize this accountable safety to rollups? So in the case of rollups, I would like to say that when there is a safety violation on the rollup chain, all observers should be provably identify F adversarial parent chain validators as the protocol violators. So here the emphasis is on the parent chain validators. So now you might ask, okay, in this notion of accountability for rollups, why am I identifying parent chain validators and instead of identifying, let's say, like rollup nodes? Well, the reason is I would like the accountable safety to give me an economic notion of security. So these parent chain validators are staked in the parent chain protocol, which means that when they engage in a safety violation, if I can provably identify them, I can also financially punish them by slashing their stake. And this slashing basically acts as a deterrent, hopefully, so that they will never be doing this safety violation. That is why parent chain validators should be identified, even in the case of a safety violation on the rollup. Now, in the remaining part of the talk, I will basically prove accountable safety for a rollup and see what assumptions are needed. But as a reminder, before I go to the proof, let's see that consensus and data availability were the responsibilities of the parent chain, and execution was the responsibility of the rollup nodes in the case of a rollup, or rather verifying the execution was their responsibility. Now, going back to this, the list, we can see that there are three main ingredients again for a rollup, and we can see that the safety violation can happen due to a failure of any of these three ingredients. So in the proof, I will basically go through safety violations that happen due to failures of these pieces. So the first one is consensus. So in this case, what might happen is that here is our parent chain, and here is our rollup chain that's corresponding to the parent chain. So suppose there is a safety violation on the parent chain, which might induce a safety violation on the rollup chain, because now two different clients might think the second rollup block should be either ST2 prime or ST2. Now, this setting is kind of benign for our definition, because in this setting, we do indeed have a safety violation on the rollup chain, but we will be able to identify 1/3 of the parent chain validators as protocol violators. And indeed, how this happens is that I will again inspect the two parent chain blocks. And if the parent chain itself provides accountable safety, now this is our first assumption to provide accountable safety for rollup, is that the parent chain should provide accountable safety. Then in this case, I can identify the validators who double signed these two conflicting blocks. So far so good. Now let's see a safety failure due to execution. Here is our parent chain. As you recall, in a sovereign rollup, there might be invalid rollup blocks accepted by the parent chain. And an adversary can claim that this invalid rollup block should be the second rollup block. However, I'm actually cheating a little bit in this example, because this block will not be accepted by the rollup clients. Because when rollup clients or nodes, when they execute these rollup transactions, they will see that the state ST2 prime is an invalid state commitment. And they would know that ST2 should be following ST1 because it's the valid one. So in this case, we actually don't have a safety violation. Okay, so far so good. Now let's come to the last piece, and this is the most important part, safety failures due to a data availability problem on the parent chain. So here we see our parent chain and the rollup chain. Now suppose there was a parent chain block that was finalized by an adversarial majority on the parent chain, but a part of its data is unavailable. Note that this part of the data doesn't cover the rollup. So the rollup's data is actually available, but some other data is unavailable. As a result, the rollup nodes or the clients, they don't notice that there is a data unavailability issue on the parent chain. and they will accept this block st2 prime tx2 prime as the next valid rollup block, extending the first block rollup block. Okay, so the clients are currently at this point, but the validators of the parent chain, they do know that there is a data unavailability issue because some of them might need the transactions here, so they will notice something is wrong with this block, and it should have never been finalized in the first place. However, because now the validator set is malicious, it has finalized an unavailable block, they also know that they cannot make any progress with this parent chain anymore. So what they would do is that they would probably engage in a social consensus mechanism. They will kick out these adversarial validators out of the system, and they will inaugurate a new validator set. And this new validator set will be finalizing new blocks, extending the last available block from the parent chain's history. Now, this is a problem though, because if there is a late coming rollup node, this late coming rollup node would think that maybe this st2 tx2 rollup block is the correct rollup block to extend the first one. So again, we have a safety violation on the rollup chain. Now, we also seemingly have a safety violation on the parent chain, but can we actually identify the adversarial validators on the parent chain? Well, that is not really true, because what might happen is that when you try to identify who is malicious on the parent chain, these malicious validators might release the data that was initially hidden, right? It was initially hidden and now it's released. And these two blocks have two distinct validator sets due to the inauguration of a new validator set by the social consensus. So there are no double signatures, and it's from an outside client's perspective who is late coming, the validator sets on those two blocks can have like equal probabilities of being adversary. So this late coming client cannot provably identify the adversarial validators. Now, if you want to learn more about these data availability issues and the unidentifiability problem here, you can check out this blog post by Vitalik on the fisherman's dilemma. Now, that tells us something though. So initially, when this block was assumed to be the second rollup block, the data in the parent chain block was hidden. So this tells us that there was something wrong with this parent chain block, and the rollup client should have never accepted this st2 prime tx2 prime block as the next valid rollup block. So as a result, if these rollup clients somehow have a method to check for the data availability on the parent chain, they would be able to reject this block, and we would never have the safety violation in the first place. So this brings us to the final ingredient. We now have noticed that the rollup nodes must check for the availability of the parent chain blocks. Otherwise, we will have this safety violation, and we won't be able to provably identify any adversarial validators on the parent chain. However, these rollup nodes cannot simply download all the parent chain data to check its availability, because that would defeat the purpose of scalability. As a result, they might be using a new technology called data availability sampling. There has been some research on this, and there's still research being done in both industry and academia. And these solutions are typically built on error correcting code. So here are some papers if you're interested in learning more. So I would like to simply end with a theorem. So our theorem basically states that the rollup satisfies accountable safety with resilience F if the parent chain is accountably safe and the rollup full nodes check for the availability of the parent chain, and it's similar for the like clients. Yeah, I think I'm out of time, but thank you very much.